I'll ask at this point, does anybody have any specific questions before we get into some of the review? We're on chapter 7, and chapter 7 is kind of the meat and potatoes of everything. It's when you get into the math, which I know, Destiny, you love to death, right? All of the math problems. So hopefully,
Dying, dude. I'm dying.
well, after you've
It's
done,
not good for an artist's brain.
after you've done 700 of them, they're quite easy. So,
Oh, great. Only 600 to go.
yeah. Okay, so let's see. Which would you prefer? Would you like me to jump into the labs and maybe walk through some of the labs, or do you want me just to go straight into the quiz?
Can we do the first lab? I started it the other day and I started picking up on it again earlier today. I inputted all the numbers correctly. Let me get to, oh my gosh, now I'm confused.
Okay, so you're talking about sizing the array lab here?
Yeah, the sizing the array lab.
Okay.
I put in for the right location, the pitch, all of that, and I even ended up following after I got the answers incorrect, like, you know how you screenshotted what my PV Watts online tool should look like? My answers were not coming out to what yours were, and I inputted all the information spot on with what you had.
All right, so let's just say that if the pitch of the roof, in this case, we've got a home in Greeley, Colorado. I picked that because that's where I was born. And you've conducted a site visit. You have the following information. So the pitch of the roof is 23 degrees. And the azimuth, or the orientation, is 156 degrees. So 156 is, 180 is true south, 156 not quite true south. And then we've got the monthly average consumption, which we would have gotten off the electric bill. And then we say we know that we're going to have to derate it by 7%. So it says, what size array would you require to fully meet? Okay, so the way we do this, let me make a note of this. It's 23 degrees, 156, 1350, and 7%. All right. So your first step is going to go to PV Watts. So we're going to go into PV Watts. And so we'll just say here. And the first thing you're going to have to do is say Greeley, Colorado. And it's going to look, and it's found the right spot. So then we're going to come in and we're going to, we won't care about system losses at the moment, but let's go ahead and say it's 23 degrees pitch or angle, and it's 156 degrees orientation. So we'll click here, and now it's going to tell us that we have 5.59 hours of insolation. So are you with me so far? That's the average. And what this means basically is every square meter of land is going to get on average 5,590 watts hours of energy. And so we divide that by 1,000 watts per square meter, which is standard test conditions. So we have 5.59 hours on average. In the wintertime, we have less. Summertime, we have a little bit more. But based on the pitch and the orientation, it's telling me how much sunlight that array is going to be receiving. Okay? Everybody there so far?
That is not the answer I'm getting.
That's not the answer you're getting?
No.
What?
No.
Did you put in the right location?
Yes, sir.
You got
Greeley,
Greeley.
Colorado. Yep. DC System 4, module type standard fixed open rack.
You can ignore this for right now because that's for your loss calculation, or you could just say 7. It won't really make a difference because we said 7%. It was a 23 degree tilt.
Yep. With
156
156 azimuth.
Okay, so then you click
Yeah,
here. And
and
now
I'm
it's
getting 5.68 is what I keep getting for my calculations.
really,
Yeah.
huh, weird. No, it should be,
Greeley,
well, I'm
Colorado.
getting 5.59.
Okay, well, obviously we'll go with what you have because it goes with the test. I don't understand though why mine's not
Yeah, there's
doing it
something
correctly.
clearly on your screen here that's not quite right. I mean, you really should only be seeing what you're seeing right here. So why don't you, try it again and see, as long as, I mean, maybe have you switched these? No, that wouldn't make any sense.
Mm,
All right, so we'll jump in here. We've got the
sorry.
5.59 hours. So then we're gonna jump back, and so what do we need to know? Well, we know that we've got 1,350 kilowatt hours per month, right? But we
Yeah.
need to know kilowatt hours per day. So we've got 30.5 days per month. And if somebody's got a calculator, this would be helpful. What's 1,350 divided by 30.5?
44.26 kilowatt hours per day.
44.26 kilowatt hours per day. Okay, so that's how many kilowatt hours per day. And we know that we have 5.59 hours of insolation, should be kilowatt hours, which is why we've converted it to hours. So 44.26 divided by 5.59.
Is 7.92 kilowatts.
Yeah, 7.92 kilowatts, right? Because we got rid of hours per day. So those are gone. So now we've got kilowatts. This would be the size of the array if the array were 100% efficient, but it's not. We've been told that it's 7% loss, so we would divide this by 0.93. It's only 93% efficient, so we get 7.92 divided by 0.93. So we should get a number that's bigger than this. We end up at
8.51 kilowatts.
8.51 kW. So that should be the size of our array. So if we go back to our to our quiz here, or our lab, and I go to this screen, and 8.51 is one of the options. And let's just double check that that's right. And there we go. So it's telling us that we've got those numbers plugged in. We get the 5.59. And then, of course, we just do the math like we did. Okay, so it sounds like your problem was just in the PV watts, getting the wrong number for whatever reason. Yeah. I don't know. Make sure that you're plugging in Greeley, Colorado, because that, I mean, you'll get different numbers in different locations. So,
No, right.
mhm.
I've been doing this all morning and I keep getting 5.68 watts. And anyways.
Huh. Okay. All right. Then the next question here is, how many panels would be required to fully meet that load demand? Well, we now know, what was it, 8.51 kW?
Mm-hmm.
So that's going to be 8,510 watts. These panels that we've selected are 310 watts each. So you just divide 8,510 by 310, and we get what number?
28 panels.
All right, so that's pretty straightforward.
Mm-hmm.
Correct. There you go. And then, oh, this is the same question. It's asking again.
No, now
Oh.
you're in Seattle.
Yeah, now if it were in Seattle, what would be the issue? So once again, at this point, we would just simply go into PV watts.
Change location.
I don't know why I keep getting out of that. Yeah, so we come back here, we can change our location. It was Seattle,
Mm-hmm.
and everything else was the same. Might require that I put it back in, yeah. 23 degrees and 156. And now we're getting 3.93. So there's quite a difference, 3.93 hours of insolation versus in Colorado with 5.59. So we would just simply, to figure that out, go ahead and clear. So we would take, once again, we know that it's 1,350. Got actually 1,350 kilowatts hours divided by 30.5 days per month. Gave us, we already had that, but what is it again?
44.26.
And that would be kilowatt hours per day. And then now we know it's 3.93 hours of insolation per day. So we get 44.26 divided by 3.93. It's going to be somewhere around
The
11.
answer is so wrong. Yeah. Oh, yeah. Then it would be 11.2. So then
kilowatts. And then that's if it's 100% efficient, but it's only 93% efficient. This is your D rate. And it equals
12.
12 point something.
Oh, yeah, 12.1.
12.1 kilowatts. So you needed a much bigger system in Seattle than you did in Greeley, Colorado.
And is that just due to the fact that there's going to be less hours of sun, there's less insolation?
Yes. Yes, exactly.
Okay.
So in this case, it's well, it's asking us how many panels would we need. So we would take that 12.1, 12,100, divide it by the 310, and now we're going to need, what is it, somewhere around 40?
Yeah.
Because we needed
39.
20.
Yeah, it would be like 39.06. So round it up to 40.
Yeah. All right. Yeah. So what you find though, and this is an interesting issue because you might then take that away and say, okay, well, solar makes sense in Greeley, Colorado, but it doesn't make sense in Seattle, Washington, because it's so much more expensive because of the lack of sunlight. You know, there's less sunlight. And if you've ever been to Seattle, you know that's true. But solar panels are only about a third of the cost of the materials in a solar installation. And materials are only about half the cost of the installation. So additional solar panels are only an incremental cost on 1/6 of your cost element. So the fact that I have to put in 12 more solar panels in Seattle versus Greeley, Colorado, may or may not be a deal breaker. It may only add, say, 10% to the overall cost of my system. What is usually the deal breaker is how much does your electricity cost? So for instance, one of the reasons why in Seattle, they really don't install that much solar is because electricity is so cheap. They have the hydro resource there from the rivers. So their electricity may only cost about 8 cents a kilowatt hour. And so it just doesn't make as much sense as, say, someplace like Honolulu, Hawaii, where they're paying 30 cents a kilowatt hour. So the additional, usually the big defining factor is how much does your electricity cost, not how much sunlight is available in your location. So, all right.
Can I ask you a question?
Yeah.
Why isn't calculating the D-rate factor included in this chapter? Is it always just given to you or assumed?
Well, there is a tool there that you can use in PV Watts for calculating D-rate.
Okay.
But there's, it usually ends up being that once you've installed a system, you get a sense of it, you know, so it doesn't have to be an exact number, but it's always going to be, well, I was going to say it's always going to be about 10%, but that's only with string inverters. It's going to vary. It really almost in today's marketplace, the only D-rate factors you have to worry about are going to be your inverter inefficiency and voltage drop. So if you've got a 98% efficient inverter and you're going to have 2% on your voltage drop, well, there's 4%. And then I usually throw in 1 or 2% more just to under promise. So at that point, I just throw in a 6% D-rate. So it depends on whether you're installing microinverters or optimizers or string inverters. So calculating D-rate, it's important, but it's more of just getting a feel for it as opposed to doing it, you know, with a strict formula. Does that make sense?
Okay.
Because a lot of times they want you to D-rate things that I don't really think that are factors like system availability. Well, why would I mean, really, am I going to factor in that the system is turned off 2% of the year? You know, why would I anticipate that? That may be the case, or it may be zero. It's something that's not in our control.
It seems like an important number in the calculation to just not know specifically, I guess.
Yeah, it is important. It gets more important if you're talking about a standalone system, because then you have to add like 15% for the battery round trip inefficiency, things of that nature. So it may be worthwhile me putting in a D-rate lab. I guess in my own practice, it's just that you just kind of throw in a 7% number or a 6% number and don't give it a whole lot of thought. But it would be easy to do. I know there's a lesson, you know, in your chapter 7 that talks about how you would calculate it, you know, how all the different factors involved in D-rating. So there's a lesson there, but just not a lab. Okay. Destiny, did you want me to run to one of the other labs, or do you want me to do that? That was the only
You
one.
go ahead and do what you got to. Yeah, it's just because I keep getting the wrong numbers in there.
Did you just try PV Watts again?
Yeah, I was doing it the whole time you were doing it. And I don't know, I can't tell you why.
You still got the same wrong number, huh?
Yes, all day long. I've been going through them. I've been getting different.
Huh. Okay, well, maybe at the end of the call, you can, I don't know if you're able to share the screen or not, but afterwards,
Looks like it.
we'll have you share the screen, and then I'll look and see if I can see what's going on. All right,
Okay.
so let's jump in here to the string calculations lab, because string calculations usually give everybody heartburn. So in this case, we're taking the array that we calculated for Greeley, Colorado. We said 8.51 kW. We're using the PIMAR 310s, and we need 28 panels. So we've already calculated all of that. Now what we're wanting to figure out is what is the maximum number in a string and what's the minimum number in a string if we're using a string inverter. So it's giving us some specifications. We have to get this from the panel specs. So we know it's 310 watts. That's at the maximum power point. The VMP, which is the voltage at the maximum power point, is 32.6. The IMP, the amps, is 9.51. If you just tested it, 9.51 times 32.6 should equal 310 or thereabouts, because, you know, watts equals amps times volts. The VOC, 40.9. The short circuit ISC, 9.8. Module efficiency, we don't need to know that, but they're going to give it to us. And then we have some temperature coefficients. So the temperature coefficient on this panel at Pmax is plus or minus 0.42% per degree Celsius. What that means is that for every degree Celsius more temperature than standard test conditions being 25 degrees, then that panel is going to produce 0.42% less voltage. For every degree Celsius less, it's going to produce 0.42% more. If we start at Pmax. If we start at VOC, then the number is 0.32. We'll end up at the same thing, but the reason that they're giving you these will become apparent when we talk about minimum and maximum. So when we're trying to figure out what is the minimum number of panels that can be connected, well, this is randomizing it, but normally we'll start with max. But in this case, let's just say the minimum number. Well, the issue that we have with minimum number is it's being hooked to an inverter. And that inverter needs a certain amount of voltage to start. Otherwise, it's just going to assume like it's nighttime and it's not going to generate any power. So this one here, the inverter we have, has a minimum voltage of 180 volts DC. And we know that the warmest day ever recorded at this site is 38 degrees Celsius. So let me write these things down. It's 180 volts DC. 38 degrees Celsius is our temperature. And assume that it's mounted flush to roof 6 inches from the deck. All right. So, and the reason this hint down here is going to tell you that for 6-inch flush to roof, we're going to have to add 35 degrees to the ambient air temperature. So let me jump into the calculation screen here. And what we're, okay, so we start out, well, with maximum and minimums, we always start at the delta, or the difference between standard test conditions, which is 25 degrees, and it said the hottest temperature ever was 38 degrees. So the difference, the delta, is going to be 13 degrees Celsius. The difference between those two numbers. But because it's a flush to roof, if you've ever worked on a roof, you know that it's hotter on the roof than the ambient air temperature. So we're going to add 35 degrees. So we have 13 plus 35 gives us a delta of 58 degrees Celsius. And it said for every degree Celsius, when we start at VMP, or the voltage, or the Pmax, because on this we want to estimate at the lowest end. So for the minimum, we start at VMP. And that was, if my memory serves, it was like 0.42 per degree Celsius. So the temperature coefficient is 0.42% per degree Celsius times 58 degrees Celsius.
I'd use 48.
It's
So
48.
Oh, it was 0.48? Oh, 48? Yeah, you're right. You're right.
No, no.
That's good. I was just testing you guys. All right, so 0.48. So what is the answer there? .42 times 0.4 times 48.
17.
20.16.
20.16. Does everybody agree? I always like to have
Yep.
two people do it. All right, so
Especially not me, guys.
so it's saying that on the
For
hottest.
2%, would you have to move
What's that?
for 0.42%? You don't have to move the decimal point over twice to say 0.0042 times 48.
Well, that would give you a decimal. We're wanting to know percentage at this point, so we're going to keep the
We
percent.
do 1%.
Yeah, so this is going to
Okay,
cancel this,
gotcha.
and we'll end up with a percentage. Now, we will have to change that here in a second. So we know that on the hottest day ever, this panel will produce 20.16% less voltage than it would under standard test conditions. Well, what was the VMP on that panel? I forgot. I didn't write it
The
down.
VDC?
Yeah,
I think it was like
It was 180.
32.5.
yeah, 30, the VMP, because we're going to be dealing with actual voltage here, is 32.6. So I'm going to write that down.
32.6.
32.6 volts. So that's our voltage. So normally the panel is going to produce 36.2 volts under standard test conditions, but because it's hot, it's going to produce less. So I would multiply this times 100% minus 20.16% or 0.7984. Is that right?
Yeah.
79.84%. So what's 36.2 times 0.7984?
Is it 36.2 or 32.6?
It's 32.
Oh, it was 32.6. Yeah. It's a dyslexic panel here.
27.16.
27.16 volts
Yeah.
DC. So what this is saying is
I
that
got
on the hottest,
26.8.
Yeah, I got 26.02.
Just when you change it from 36 to 32, it takes it down to 26.
oh, okay.
Yeah.
All right, 26.02. So it's saying that normally
Yeah.
under standard test conditions, this panel would produce 32.6 volts, but because it's hotter, it's only going to be producing 26.2 volts. Well, our startup, we need 180 volts to start that inverter. So how many panels do I need to hook together in a string to make sure that thing turns on?
7. 6.9177.
6.91. Yeah, and we would round
Yeah.
up because we want it to exceed. So 7 panels minimum. All right, so that's how we would do our string.
Per string to start that inverter.
Yeah, that's the minimum. But then we need to know, well, what's the maximum? So what's the most we can put in a string? So we know it's going to be 7 here. Okay, so the next question, this gets into all of that. Yeah, I'm just going to guess wrong. I don't want to go into all that. You guys can figure all that. All right, so now what's the maximum? Well, assume that the maximum voltage limit on the inverter is 600 volts. Well, now instead of dealing from the VMP or the maximum power point, we're going to deal with the VOC, which is the theoretical maximum. So because we're wanting to make sure we do not exceed 600 volts, we're going to go with the worst case voltage issue. So we're going to be dealing from 40.7 volts, which is the VOC, and the temperature coefficient at VOC down here is 0.32. All right. So if we go back into our calculations, where we had figured out 7 panels minimum, well, now we start at the delta once again. So STT is 25 degrees Celsius. And, oh, what was the coldest day? I didn't.
Negative 18. degrees
Negative 18?
Celsius.
All right, so negative 18 degrees Celsius. So the delta between the two is actually going to be 43 degrees.
Yes.
Okay, and then the temperature coefficient at VOC was 0.32% per degree Celsius. So that's saying that this panel will produce 0.32% more voltage for every degree Celsius you get below 25. So now 43 times 0.32 gives us what?
13.76. 13.8.
Okay, so 13.76% more volts. Well, we take our VOC, which is 40.7 volts, which is our VOC, times 113.76%, or decimalized, that's just going to be 1.1376. And we get
46.3.
46.3 volts. All right, so on the coldest day, it's going to produce 46 volts. On the warmest day, it's only going to produce, what was it, 20 some volts? So it's quite a difference based on temperature. Well, we cannot exceed 600 volts. That's the maximum for the inverter. We divide 600 by 46.3, and we get
12.9.
12.9. So we would round down 12 panels max. We round down because we don't want to exceed it. So it was 12 panels maximum, 7 panels minimum. And we needed 28 panels total, right? So how would we configure this array? Well, each of these strings has to be balanced. So it's looking to me like 28 doesn't divide evenly into anything except 14. So we can't do 2 strings of 14 because we can only go 12 max. So if we did 3 strings of 12, well, we're only at 26. So do we undersize our array a little bit? Or, I mean, that's an option. And that's going to be your call as a designer. Or do we do 3 strings of 10, which gives us 30, and oversize our array a little bit? Those seem to be really the only options for this. So some of the factors.
And we'd want to
Would you-
oversize it, right?
Would you not want to do like 4 strings of 7? You don't want to ideally hit your min or your max. You'd like to be right in between them. for
What
the
you
string.
could do 4 strings of 7. The problem is you're going to then increase the cost of your system. because your amperage is going to be lower, so your wire is going to be bigger. You're going to have 4 connection points, like 4 circuit breakers in your inverter connections. So usually you want to push the voltage as high as possible. But you're right, in this case, we could do
Okay.
four strings of 7. That would not be my ideal option. I would really try and go
Okay.
either 3 strings of 10 or 3 strings of, what was it? Two strings. Well, it'd have to be 3 strings. We're not going to be able to get 2 strings unless we go to 24 panels. And that would be quite undersized. So some of the issues that you would be looking at is this home, like the homeowners, are they going to be using less electricity in the future or more electricity? So let's say they've got teenage kids that are just getting ready to move out of the house. Well, they may be in a situation where in the future they'll be using less electricity, quite a lot less. If they're younger and have kids, they may be using more. They may be thinking about buying an electric car. Now, you'd also want to check with your local utility, because if they penalize you for overproducing, you don't want to overproduce. You know, if you're overproducing their usage, you might fall outside of the net metering laws. So that's something that you're going to have to evaluate as well. So there's a lot of, art to all of this. You can't just say one size fits all. You've got to evaluate that individual circumstances before you could make the decision. Okay, does that one make sense? That one's usually, I would say, of all the math questions, string sizing is the one that tends to confuse people most. There's a lot of little factors in there that you have to fiddle with. One of the nice things about microinverters is guess about how you size the strings. 28 panels, 28 microinverters, string sizing is done. There is none of that calculation involved. And with power optimizers, they're usually going to tell you in the spec sheet, okay, if you use this optimizer, you can't hook more than 15 of them together in a string. And so it's not something that you can calculate or that you will calculate. It's just given to you in the spec with the equipment. So that's one of the nice things with optimizers and microinverters. You don't have to go through all this hassle with string calculations. But it is something you need to know, if you're making this your life. So, all right. I'm going to jump down to some of the quiz questions here, and we'll hit a few. When we get right on the, a couple of minutes before the hour, we'll go ahead and call it, because we're going to spend a couple of these sessions on Chapter 7, because this is one that you really need to understand, spend some time on. So, which of the following is not a circuit in a typical grid-tied PV system? PV input, PV output, inverter output.
PV input.
PV input. Yeah, and I wanted to just show you what I mean by a circuit here. So in a typical grid-tied system, you're going to have your array, and then you're going to have your strings going into either a combiner box or a junction box. So if this is your combiner box, then it's going to go from here and it's going to go to your DC disconnect. From the DC disconnect, it's going to go to your inverter. And then from the inverter, it's going to go to an AC disconnect. And then from the AC disconnect, it's going to go into your service panel. This is the main, that's the meter, and then it goes out to the telephone pole and the transformer. Okay, so when we talk about circuits, the circuit that's between the panel and the junction box or the combiner box, this is called the PV source circuit. It's the only circuit that's not contained in conduit. It's going to be the loose wires that are connecting to the backs of the panels. Now, hopefully you'll use straps and things and attach them to the rails. Then from the combiner box to the DC disconnect is called the PV output circuit. From the DC disconnect to the inverter is the inverter input circuit. And then from the inverter to the loads is the inverter output circuit. And we just simply have these labels because there will be situations where you will refer to these areas and each one has different properties. But this is the way it is normally with a standard grid-tied system. And there is no PV input circuit, as the question indicates. I always like to say the PV input circuit is the sun, right? Okay, so which of the following is not a factor in determining the size in amp hours of a standalone system's battery bank? The daily system load requirements, the nominal voltage of the system, peak sun hours, or the depth of discharge?
Depth of discharge.
Depth of discharge, everyone agree? Let's say peak sun hours. All right, and the reason for that, let me just do a quick calculation on figuring out a battery bank. So in your book, it'll tell you the process here, but with a battery bank size, the first thing you need to know is what is your daily load? So what's the daily load that you're wanting to service from your batteries? So let's just throw a number out here. Let's just say that it's going to be 10 kilowatt hours. That's our daily load. Now, batteries are sized in amp hours. So how do we get from kilowatt hours to amp hours?
Use voltage.
Yeah, we would divide by voltage. Yeah, so let's assume our system is 48 volts. So what's 10,000 watt hours divided by 48 volts?
A little over 200.
That's 208.33.
208.33. And that's now going to be amp hours. So we divided our daily load by our system voltage. And now we know the amp hour capacity. So you might be tempted to say, okay, well then I just need a 208 amp hour battery that's 48 volts. But now we have to divide this by the depth of discharge. Because with lead acid batteries, we can't use all of the battery. So let's assume that we're going to use 60% of it. So we're going to go 60% depth of discharge.
0.6. Oh my.
So what's the number?
320 then,
320, is it?
roughly.
No, it's 347.22. I did it correctly.
Okay, 347.22 amp hours. All right. The next thing we need to do is derate it. Let me see, I'm doing this by memory. I haven't done it for a while. I know we have to derate it by, oh, we need to know, all right, yeah, we derate it by the inverter's inefficiency. Well, why is that? Well, if this is our standalone system, we've got our combiner box, DC disconnect. We come in here to a charge controller, come to our battery bank. Now we're going to the inverter. And then we're going to our loads. All right. Well, what is the only piece of equipment between the battery and the load? That's the inverter. So the only thing we have to derate in this system is the inefficiency of the inverter. We don't have to worry about anything that comes before the batteries as far as inefficiency. So we're doing our derate, and let's assume that we've got a 95% efficient inverter. So what's 347.22 divided by 0.95? Should be somewhere around 360, 370.
365.5.
So 365.5 amp hours. All right. Now, the last question we need to ask ourselves is how many days of autonomy do we want this system to function?
And Baptist minister.
So we're saying that, okay, this will take care of 1 day, but is 1 day enough? You know, what if this is a weekend cabin? Well, that may not be a big deal, but if it's a hospital
The light everywhere.
or something like that,
That's just me.
then you might need to have multiple days. What if it's only a part of a day?
Overthinks everything. Another friend's
So-
gonna describe me as a hoe.
This is Will.
Okay.
A lost
I'm getting some feedback from somebody there, so some background noise. Okay, so let's say it's 2 days of autonomy. But it could be half a day, it could be whatever. So 2 days of autonomy, now it's going to be 700.
Dixie dating Griffin Johnson.
And-
That's what everybody wants to know. She is. Okay,
What is
so
it,
that's the initial then.
730? 731?
Yeah. Okay. Wow. Okay.
Is that right?
That's definitely a good. It's Dixie dating Griffin
Hold on.
Johnson. That's what everybody wants to know. Yeah. She is. Okay. so
Times
that's the initial
2.
then.
Yeah,
Okay, wow. Okay, that's definitely-
730.98.
Okay. So at this point now what we would do is we need to go out and select a battery. So let's say that I'm going to select a battery and I'm going to just go out here on the web and I'm going to say 700.
Whoever's watching videos, you're killing me, Smalls.
If you could mute your mic or whatever, if something's on. All right, so I'm looking for a 700 amp hour battery. So I'm going to have to go and do some. That's not going to be it. Let me put deep cycle. I just threw 700 in. Yeah, let's pick this guy and see what it is. This one may not be required. It's a 6 volt. Yeah, this is a 6 volt, 224 amp hour battery. So they use this, I guess it's a forklift type thing. All right, so just to get a sense of the size of this battery weighs 68 pounds for each one of them. So it's 6 volt, 224 amp hours. And again, just for a sense of it, what was the price? Oh, 5% off. That's a deal. 325 bucks, basically. All right. So we need 723. So how many batteries if we selected that one? 731. Each battery, 224. So it looks like we're going to need 3 strings, right? It's not going to quite get us there. Maybe 4 strings. that right?
Yeah, it'd be about, 4 strings.
4 strings. And it's 6 volts. Well, our system is 48 volts. The battery is 6 volts. So how many batteries in a string do we need?
8.
Yeah, 8 per string. So I need 32 batteries at $325 each. So that's going to be somewhere in the neighborhood of $1,000, right? No, $10,000. Is that right? 325 times 32?
Yeah. Oh,
They're about 10,000.
yeah, about 10,400.
$10,400 just for our batteries for a system that's providing 10 kilowatt hours per day. Now, the average home uses 30 kilowatt hours per day. So we're talking about a very small cabin type facility or 1/3 of a typical household load. And it's going to cost you $10,000. And those batteries probably have a life expectancy of around 5 years. So every 5 years, you're going to have to spend another $10,000. This is one of the reasons why everybody hooks up to the grid, because the grid is an awfully cheap battery. The downside, of course, is that if the grid goes down, you don't have power. Because with a grid-tied system, it's designed to shut off as soon as it loses sight of the grid.
And you're grid tied over at Blue Rock, right?
Yeah, ours is grid-tied, and it's
I don't remember seeing a battery bank anywhere.
no, there's no battery bank. I do have some solar generators that I can use as an emergency backup, that I would have to wheel around and plug in my refrigerator or my freezer. That's kind of the poor man's battery backup system. I want to rig up a golf cart where I can just simply have a solar powered golf cart and then just drive it to wherever we need the power and just run an extension cord from it. That'd be kind of cool. I have this vision, we'll paint it like the Partridge Family bus or something, make it real funky. Okay. All right. A standalone PV system has the following characteristics. A 3 kW array, daily load demands 10 kilowatt hours, a maximum power draw of 2 kilowatts at any time, a 1400 amp hour battery bank, a nominal battery bank voltage of 48 volts, and 4 hours of peak sunlight. What is the minimum power rating required for this system's inverter? Now, this looks like it's a very complicated question. It's actually quite simple because there is only one parameter that you need when you're sizing an inverter for a standalone system. That inverter has to meet the daily load demand or the maximum power draw. It's got to be sized big enough to handle all the power flowing through it. Okay?
Should be 2 kilowatts.
Yeah, so the minimum size, the smallest size is going to be 2 kW. Nothing else here is an issue when we're sizing the standalone inverter. So it's just a lot of information that you don't need to have. And that brings me to a point that I think it's critical that you understand with a standalone versus grid tied. Okay, and it's just conceptually how power flows. So if this is going to be a grid tied system and we're going to our junction box, we go to our DC disconnect, and then we go to our inverter, from the inverter to an AC disconnect. From the AC disconnect, we're going into our load center. And then from the load center, this is the meter to the grid, okay? And from here, these are our loads. So think about how the power flows. Basically, when you turn on a light, the power is going to flow from the array to the load, okay? Now, if I have more power available than load demand, the excess power is going to flow out onto the grid. So it's going to be flowing in two directions. All of the load that we need to fulfill all the power we need to fulfill the load demand is going to go to the load. Any extra is going to flow to the grid. And this happens automatically. It's like water finding its level. Energy, the power will always flow to the lowest, to the least path of resistance or the lowest impedance. So a load, when you turn on a load, you can think of it like a low pressure system or a low pressure area, and the power will flow into it like a hole until that hole is filled, and then it's going to flow to the next lowest place. Well, in this case, the grid is at a lower level of impedance than the array because it's generating more power, more voltage. It's sort of like if you had a bucket or a barrel of water here, a rain barrel, and it's full. If I were to drill 2 holes in the side of this barrel, well, water is going to flow out here, and it's going to flow out here, and it's going to keep flowing out. Well, how does it know which hole to come out of? Well, it's just gravity, right? It's just a natural force. So the same is true with electricity. It's going to flow here, and it's going to flow here. Now, once the water level has fallen below this hole, it will no longer flow out of there. It will only flow here until the water level is below that hole. So it's the same kind of thing over here. So now, what would happen if the load was greater than the amount of power coming from the array? Well, then it's going to make up for it by coming from the grid, because now your loads are at a lower level of impedance than both the grid and the array. So it's going to flow this direction. Okay, so notice all the power that's flowing from the array is flowing through the inverter. So in a grid-tied system, this one here is grid-tied, the inverter has a relationship with the array. It has to be sized in a way that is proportional with the array itself. It has to be able to handle all of the power that's coming from the array. But it doesn't care what your load demand is, because either it's going to meet it or it's going to be subsidized by the grid. So the inverter really doesn't care what your maximum power draw is, what your load demand is. Really could care less. Does that make sense? Its issue is to take
pulling
all
it from the grid.
Its issue is to take all the power from the array. It doesn't care about loads. Now, the opposite is true with a standalone system. With a standalone system, we've got our array, we've got a combiner box or a junction box, a DC disconnect. Now we go to a charge controller, go to our battery bank. From the battery bank, we're going to go to our inverter. From the inverter, we're going to go to our load center, usually as the main, and now these are the loads. Okay. It's important in this to think of it as 2 different systems. Let's just draw a dashed line right down through the middle of the battery. Each side of this can operate independently of the other side. All that the array is doing is charging the batteries. And the loads are simply drawing from the batteries. So power is being pushed from the array to the battery, and then power is being pulled from the batteries to the loads. Now there can be a little bit of spillover if you've got it, but let's not confuse the issue. All right, so the inverter doesn't care what size the array is. Has no relationship with the array at all. Could care less. The array is there only to keep the batteries charged. But the loads have to fully be serviced by the inverter because all power that's going to load is being drawn through the inverter. So let's say that I turn on 4,000 watts of lights and refrigerators and all that, but my inverter is only rated for 3,000 watts. Well, it's like blowing a circuit breaker. I've overloaded it. That inverter is going to let out a squeal and shut off because too much power is trying to be drawn through it. It is not sized to handle it. So I better make sure at minimum I've got a 4,000 watt inverter if I think my maximum power draw is going to be 4,000 watts. Now, these inverters do have a surge capacity because like a lot of your loads, if you turn on a refrigerator or a motor, it's going to have a brief couple of second surges. So a 4,000 watt inverter will have like a 5-second surge of up to 8,000 watts. But let's just ignore that for the moment. At minimum, you want to make sure that your inverter is sized to your maximum power draw. And just to be safe, you usually want to give yourself about a 20 to 25% fudge. So if I had a maximum power draw of 4,000 watts, I would put in a 5 kW inverter because you don't want to run it at maximum. You know, that's just hard on the equipment. It's like running your car at full speed. So the relationship in a standalone system is between the maximum power draw and the inverter, and the relationship in a grid-tied system is between the array size and the inverter. So those are important concepts to understand. Have I lost anybody in this?
So what would you need to know to select the charge controller? The right
The charge controller goes between the battery bank and the array. So it would have to be sized in order to handle the amps coming from the array. And it would also have to be sized in such a way that the output voltage matches the voltage of the battery bank. So the input voltage, pardon?
Is that nominal voltage?
Typically we're referring to them as nominal voltages. So for instance, in a standalone, it's easy to conceive if this is a 48 volt array, then you need a 48 volt nominal charge controller, a 48 volt nominal battery bank, and a 48 volt nominal inverter. All of those would have to be rated to be compatible with each other. And that's all the nominal voltage rating is saying that that piece of equipment is compatible with a 48 volt nominal battery bank. Everything keys off the battery bank. So the voltage ranges might be substantially different than 48 volts, but they're considered 48 volt nominal because they work with a 48 volt battery bank. But anymore, what you'll usually find is that the charge controller has, it's an MPPT type charge controller or a buck boost. So you could go with, say, a 250 volt array coming in. So it'll come into the charge controller at 250 volts maximum, but it'll leave at 48 volts. And the reason we do that is because the voltage drop would be substantial between the array and the charge controller. You know, you might be going 200 feet or 300 feet out into a field. So you'd end up having to use really big wire. So it's better to be able to push the voltage of your array up and then step it down within the charge controller. So this is now more the norm. In fact, they have some that'll go all the way up to 600 volts so that you could arrange your string sizes the same as you would with a grid-tied system. Okay. Now, if it were a 250 volt charge controller, then when we did our string calculations, instead of worrying about what is the maximum voltage of our inverter, we would worry about what's the maximum voltage of our charge controller. And our string sizes could not exceed the maximum voltage of the charge controller for input. Now I suspect I've lost somebody. Right.
Mm-hmm. For
So,
sure.
This is covered in the lessons, but I think you're just going to need to go over it several times. At some point it's going to click, but everything needs to be compatible with the voltages, but the voltages don't necessarily have to be the same thing. If you've got a DC to DC voltage converter within that piece of equipment. All right. With a grid-tied system, normally your array is going to be configured to a maximum of 600 volts, and your inverter is going to have a maximum of 600 volt input. So this is for residential. And the reason they're configured at 600 volts is because that is the limitation imposed by the National Electrical Code. So in this case, then we just have to worry about the startup voltage, which might be, say, 120 volts. So that's why we get our minimum and maximum string size. With a charge controller, if it was 250 volts maximum, there's usually no minimum start voltage required. It's a passive run-through system. So then you don't have to worry about minimum string size. You just worry about the maximum. So if these panels were each generating in the neighborhood of, say, after you've adjusted it for temperature, 45 volts, well, then I could put 5 in a string and still be underneath our 250 volts. All right. Hopefully this will all begin to make sense. We're in the hardest part right now, and you're learning a language, a whole new language. So don't get frustrated if it's confusing at first. Just keep going through it and then come back next Tuesday with some questions, because that'll be helpful. Or email me questions between then and now. All right, I think we've confused everybody enough for today. So let's stop it there, and we'll see everybody on Tuesday. All right.
Thanks, Jay.
Take care.
Yep.